studies in Los Alamos, to tell us about PT-Symmetric Kagome Lattices and Nonequilibrium.
All right. First of all, I'd like to thank all the organizers, Joshua, Carl, Jonathan, and Miloslav, for inviting me to this very important historical city. Number two, I'm going to give you two slightly unusual applications of PT symmetry, one in more condensed matter, and that's Kagome lattice, and secondly in what we call non-equilibrium thermodynamics. So before I proceed, here's a question for Carl. Why did Schrodinger and Heisenberg like to live in downtown? Because they didn't commute. With that, the first part of the talk will consist of Kagome lattices. As you have seen, that there has been some work on square and hexagonal lattices, but Kagome lattice is somewhat different. So we'll see what happens when we put gain and loss on a Kagome lattice. So it's a non-trivial extension, and basically what we will find is in the dispersion we'll find some flat bands and also unusual rotation of the power distribution. So that's the first thing. The second part you may not be very familiar with. The Bender-Basher PRL came out in 1998. A year before, Chris Zarzynski, who was a staff member at Los Alamos, came up with a different kind of breakthrough. How can you connect non-equilibrium work with some equilibrium free energy? And he was able to connect that for classical physics, and that is the celebrated Zarzynski equality. Later on, this was extended to quantum mechanics, that when you have the thermodynamics of nanosystems, you must invoke thermodynamics at that level, and that's the quantum Zarzynski equality. In this second part of this talk, I'm going to extend it to the PT-symmetric quantum mechanics, and that work is published with Sebastian Defner in this PRL. And the first part of the work is done by Jiawei Chern, and we'll submit it next few days here. So let me start with Kagome lattice. So this is the Kagome lattice. As you see, up front, let me make it very clear. If I just put gain and loss at the vertices, you will always be in the broken regime, so it is not PT symmetric. So we had to devise a way by putting diamonds with gain and loss in this particular fashion. So one sublattice is tilted this way, other sublattice is tilted that way. So there is a chirality built in when you put gain and loss in this lattice. Now those of who don't know what is a Kagome lattice, this is this Japanese woven basket pattern, Naomichi. But there's also a famous cartoon character called Kagome in Japan, in some maybe children know that. Anyway, so this is your Kagome lattice, comes from the baskets in Japan. So let me start with the PT-symmetric photonic lattices to begin with, and then I will introduce a PT-symmetric tight binding model, and then we'll go over to the Kagome lattice. The idea with Kagome lattice is there are many, many ground states. So you will have geometrical frustration that will eventually lead to flat bands in the dispersion, and then we'll proceed from there. So you've already seen that in PT-symmetric quantum mechanics, you got this potential, and basically real and imaginary parts have this symmetric and antisymmetric property. So now you go down from Schrodinger equation to optics. So in the paraxial equation, instead of the potential, you get the refractive index, and the time becomes space along this propagation direction. So basically this can be reduced to a couple mode equations, which are nothing but like a tight binding Hamiltonian with gain and loss. Here gamma is your PT symmetry breaking parameters. So basically this is the mapping between Schrodinger and optics, and you can find some of these in these references. So now if you take a 1D PT symmetric waveguide array with alternating gain and loss, then you have a system like this, and you get coupled mode equations like that. And basically, it doesn't come up good here, but if gamma is less than gamma c, the critical value of PT symmetry breaking, then you get this dispersion with gap right here. At exactly gamma equal to gamma c, there is no gap here. So that's the dispersion for this particular setting. And if gamma is greater than gamma c, you have broken symmetry regime and you get complex eigenvalues in that context. You can do the same in, well, anyway. So when gamma equal to 0, you have no spreading. When gamma non-zero, you will get some spreading, and same thing also happens in 2D case. You get some kind of spreading of this intensity. Okay, so now let me so you can make. So let me move on to the hexagonal lattice. So graphene, carbon 2D structure, graphene is a hexagonal lattice. Now in that graphene we cannot change the lattice parameter, but if you use laser beams to create photonic graphene, that gives us more tunability. You can actually change the lattice parameter that you cannot do in real materials or condensed matter. So people have considered photonic graphene that looks like this, and if you put T and, so these red and blue are again gain and loss, and if you put T and T prime, which are the hopping, if you put them equal, you are always in the broken regime, so you do not get anything interesting. But if you T and T prime are not equal, then you get interesting physics. So when gamma is 0, if you look at the dispersion for graphene, you will get these conical points, Dirac points, and for gamma non-zero, you will have gaps in the dispersion here, and here are the real and imaginary parts of that stuff. So, but if T is not equal to T prime, in the anisotropic case, suppose I put gamma equal to half T, so you will get some kind of gap here. Oh, well, depends on. So if you choose T and T prime arbitrarily, then you will get a gap, but for very special values of T and T prime, you do get Dirac points here. And also, if you put a Gaussian wave packet here, you will get some kind of conical diffraction which will spread into rings in this fashion. The detail can be found in these in this paper. Now people have been able to make photonic graphene experimentally, so the next question is, can they make photonic Kagome lattice? So that's what we are suggesting, and this is how you will make it, and from adjusting some of these beams in this fashion, and you get the Kagome structure. So let me spend few minutes about Kagome, why Kagome is so interesting. So let me just do magnetism for a second. So suppose I take a triangle, basically Kagome is corner sharing triangular lattice. If I put antiferromagnetism, I put two spins this way, the third spin is going to be frustrated. You can never satisfy that. What that means is that if I take Kagome lattice, one of the bonds on each triangle will always be frustrated. That means you will have many degenerate ground states, and this will lead to frustration. And if you look at the number of ground state, goes as e to the power half number of spins, which means you will have a finite entropy at 0 temperature. So this is very unique and characteristic of Kagome lattice, and the consequences when you look at the dispersion, because of this high degeneracy, you will find flat bands in the dispersion in this case. So suppose I have this Kagome lattice and I take this hopping T and I ask what is the dispersion, so I get dispersion bands like this. So let me just go through this. So you at epsilon 3 equal to minus 2T, you will get a flat band. You will get a flat band here. You will also get Dirac points here, you see at K, and you will also get Van Hove singularities at particular fillings here, and in addition you will have this quadratic bands touching this flat band. So that's called topological quadratic band touching. So these are the unique features that you will see in the dispersion of a Kagome tight binding lattice that you don't see in simple hexagonal or square lattices. So very interesting characteristics that you will observe. Now this was already known in a very different context. If you look at a paper by Haldane in the context of topological insulators, he was saying that suppose in a hexagonal unit cell, you have k and k prime, so you have these direct points, and then you do something to the lattice and you open the gap, and that is in the context of topological insulators. Similarly, in this paper you will see, now we are talking in the context of churn insulators. If you have a quadratic band touching a flat band like this and you open it, and that's a churn insulator. So this was two different contexts in which band gap opening, either topological insulator like or churn insulator like, was known. In the case of Kagome lattice, both of these things exist simultaneously, and that you can think in the following fashion, that there is a flux coming out of each triangle and -2 phi going through the hexagon. And that if you look at, so if you look at if phi equal to 0, then you get this kind of dispersion, and there are these Dirac points, no gap. But if there is a certain flux, say pi by 3, so you get these gaps, and these bands belong to different churn numbers, topological numbers, +1, 0, and -1. So Kagome lattice is topologically very unique and distinct and interesting. So the next question is, as I said, because of that characteristics, you get flat bands. Why do you get flat bands? Because you will see that you have many localized modes of this sort on a Kagome lattice. Now, if you were to look at interacting bosons in a different context, you'll find close packing of hexagonal modes. You can find in this paper. Or if you have 1/3 filling of interacting fermions on this lattice, Kagome lattice, you will see again localized modes. And finally, if you go to nonlinear optics, again on a Kagome lattice, you can see localized structures including compactons and some others. So basically, Kagome lattice prefers hexagonal kind of localized modes, and that will become interesting as we go along analyzing this. So now I'm going to look at PT-symmetric Kagome lattices. So suppose I take this lattice and start putting gain, loss, and nothing, gain, loss, and nothing on these vertices. It's always in PT broken regime, so nothing interesting happens. So we can try a different arrangement, √3 by √3 arrangement. Still nothing happens. I mean, still in PT broken regime, so we don't get anything interesting. So this was a bit frustrating, no pun intended. Kagome lattice is frustrated that we tried all kinds of things and we were not getting PT symmetry. So then we went back to the literature and looked at what people were doing in different lattices. Basically, they were looking at as gain loss dimers in many different contexts. Whether it's a chain or a ladder or a square lattice or a honeycomb lattice, it was the dimers which were giving you PT symmetry. So that was a good clue.
That's not unbroken PT symmetry. The one in the lower right hand corner.
This one?
That's broken. Oh,
yeah.
But it's a
T prime.
Yeah. I see.
T prime.
Right,
T
yes.
prime. Yes. So that was the clue that dimers as building blocks for PT symmetry in some of the lattices. For instance, in this particular ladder case, you can have an on-site potential and then ask that beta and gamma are random, some distribution. Then you will find as you increase beta, the regime in which it is PT symmetric basically decreases and disappears. And these are the corresponding coupled mode equation. So the point was having dimers on these lattices was a key to attaining PT symmetry. But where do we put the dimers? So if you put dimers directly like this, we saw it's not going to give us PT symmetry. So we tried many things and finally figured out the dimers had to be like this, perpendicular to this vertex everywhere. So you have two sublattices, gain and loss. One sublattice is tilted leftward, the other sublattice tilted rightward. Gain and loss sublattices, and this allowed us to actually finally figure out this problem. We tried many things and finally this thing gave us a PT symmetric phase. So basically two twisted Kagome lattices, and you can see those right there. So one sublattice is the blue one counterclockwise and red one clockwise, and this structure gave us a PT-symmetric Kagome lattice, and then we could do things with it. So now, gain and loss, and you see depending on where you are, so blue bond is T, red to blue shorter bond T plus T prime plus delta, and red to blue longer bond T minus delta. So you have different kind of hoppings depending on where you are located, and then you get basically these coupled mode equations.
So delta is negative, right? Is that, no?
No,
Oh, I see. It's
yeah,
T prime.
T prime. Okay, so then we have these coupled mode equations, and now we can solve this. So we can write in the Fourier transform form. You get these matrices, and the matrices look particularly like this. Here is the gamma, and all the other stuff, T prime, coupling kappa, and other things are contained in here. So we can actually solve. We can solve this and get the following dispersion. Somehow it's not looking good. My system looks good, but never mind. But you can see that, right? So again, the features I was mentioning, the first thing you get two sets of Dirac points, k and k prime, at k, and then there's also k prime. So these are the two Dirac points where you have crossings, linear crossings, and then you get two topological quadratic points here where band is touching, a quadratic band is touching a flat band, and two flat bands, one and this. So these are the features in Kagome lattice that you do not see in hexagonal or square lattice, but we had to choose a very specific configuration of dimers to get this. Now, so if gamma is below a critical value, so you are in a PT-symmetric phase, you got that, and exactly at gamma equal to gamma c, the structure remains more or less similar, except these flat bands come down, this gap goes down. The gap between the two flat band goes down. And now, if I increase gamma above gamma c but below a different value, then the structure changes. So you get real and imaginary part. So you got broken symmetry here. So this is one first phase transition from unbroken to broken. But there is another regime. If you increase the gamma further above this value, there's a different kind of broken regime. So in Kagome lattices, we get two phase transition, unbroken to a different broken regime. So that's very characteristic.
But in fact, just a couple springs, with loss and gain, have exactly
it's similar structure. Okay. Yeah.
Broken, unbroken, broken.
Good. So now we want to understand the eigenstates, whether they are orthogonal or not, and that's what we do is calculate Peterman coefficient, which basically means you left or right eigenfunctions, and then you sum over and average over all the Hilbert space. So this is the average Peterman coefficient. If it's 1, that means the eigenstates are exactly orthogonal. If it's more than 1, that means how much they deviate from orthogonality. So this is 1 over k bar, this Peterman coefficient, and as you increase gamma, you see this goes down from 1 to 0. These are some finite size effects. So, but anyway, you can see how the orthogonality changes. When gamma equal to 0, it's 1. Eigenfunctions are of course orthogonal. As you increase gamma, this orthogonality changes, the deviation from orthogonality. And that gap between the flat bands, this delta, also decreases to 0 as gamma goes to gamma c. And this is above gamma c, you have the imaginary part of the epsilon. And then there is a certain scaling. If you look at this k bar, the Peterman coefficient as a function of gamma minus gamma c, so there is an exponent about -1 as you go when the transition takes place. So there's a way of characterizing orthogonality and how this transition behaves in the vicinity of that exceptional point there. So one more thing about this system. So now we'll do some linear beam dynamics. So I'm going to first show you in the PT-symmetric phase, no gamma there, no gain and loss. And then as you go along the direction of propagation, you will see that this basically oscillates. If you look at this, it basically oscillates. So this is for gamma equal to 0. This local structure basically oscillates like this, nothing interesting. But if you look at in the PT-symmetric regime, you will see a rotation of this. This is interesting, very unusual for the Kagome lattice. So now we are propagating along the direction, and this thing rotates. You will see this is, it rotates. So it rotates but doesn't oscillate. So for gamma equals 0, it only oscillates. For gamma non-zero in the PT-symmetric regime, it rotates. So this is unusual beam dynamics for Kagome lattice. Small Gaussian thing, and then
But around some K, or
yeah.
where was this K in the spectrum?
Now I don't remember this near what point, but in the numerics we initiated a particular value, and then this is how we got it. So you're saying if we change the K, we could get a different kind of evolution?
Well, when we have done dynamics with hexagonal, I remember
Yeah.
not many years, but kind of remember that if we were observing conical diffraction,
Right.
we were observing various scenarios
Depends on K.
where the Gaussian is located. Where the
Right,
spectrum
right.
is.
So this is one particular K I do not remember, but we can try more to see what happens. Okay, so this is, since I'm reaching noon, this is the first part about conclusion for the first part. So we looked at PT-symmetric Kagome photonic lattices based on dimers, but dimers were perpendicular to the vertices, not at the vertices. And we found an exact PT-symmetric phase with two nearly flat bands. And we found non-reciprocal and chiral optical beam propagation. And what we have not discussed so far in exploring currently is possible topological phases, effect of disorder and nonlinearity in this lattice that we have not done. So that concludes part 1 of my talk. If you have some questions on this, you can ask me now, or I can switch to the next.
Any questions?
Yes.
These topological phases.
Yes.
So you have
Edge states.
So is this graphene, you have different type of edges.
Right.
In the armature, but this Kagome,
So Kagome will also have different kind of edges. So in the case of graphene hexagonal lattice, you have armchair and zigzag, two kinds of edges. So here we haven't explored that, but you're right, there will be different kind of edges, therefore different kind of topological phases based on those edges. We have not explored that. Okay, so now I want to move to a different part, and this is quite different. So now I'm going to talk about non-equilibrium thermodynamics for nanosystems and what happens when you bring in PT symmetry. So this is the work with Sebastian Defner. So basic idea is the following. In classical thermodynamics, you look at averages of heat and work at many length scales. You have phase transitions, chemical reactions, even in astrophysics. So only quasi-static processes are completely describable. Real processes, of course, have irreversibility, you have entropy production, etc. So the question is, in recent years, you have many nanoscale devices. When you have nanoscale devices, your quantum mechanics at work. So what happens to the idea of non-equilibrium thermodynamics when you're dealing with nanoscale devices? So that's one of the motivations, and also people are trying to make molecular heat engines, motors, which means how do you minimize dissipation at that length scale. So that's the motivation. So let me show you. So here is typical dissipation rate in joules per second as a function of characteristic length. So this is your steam engine length, and this is your car engine. And where we are at the moment, this is kinesin for molecular motors for transporting on RNA and molecule. You have smallest artificial motor made here, Also you can have tiny beads of micron size and move or drag. The point being, the dissipation here is in the regime of KBT, thermal fluctuation. That means fluctuations become very important. So the macroscopically, the thermodynamic law of second law of thermodynamics is not really valid. You need new kinds of fluctuation theorems, which people have already devised. And even in the quantum sense, so this is your so-called Newton's cradle. People have made analogs of Newton's cradle quantum mechanically. So here basically you have cloud of atoms in an anharmonic trap, and you let it propagate. So here you have two kinds of atoms with minus k and plus k momentum. You put them together, they go collide. So this is actually a quantum analog of Newton's cradle, and people have looked at the momentum distribution and other aspects. So all that we know classically is being explored quantum mechanically at a nanoscale. So now let me come to, so what is the main point? The main point is what Dzerzhinsky did in 1997 was, can I look at non-equilibrium work in many realizations, take an average, and he was able to show that an average over many realizations of non-equilibrium work can be related exactly to free energy difference. So this was a major breakthrough in that you connect a non-equilibrium quantity to free energy, which is an equilibrium quantity, and that is called Dzerzhinsky equality that I will show you. So that was for classical physics, and last 15 years or so people generalize it to quantum systems. Yes.
Did you get that from looking at the Boltzmann equation at finite times and not at long times?
That's an interesting question, because thermodynamic limit you have to go to long times, and here he assumed a Gibbs state, which means he assumed some kind of a long time distribution, I think.
Okay, so
yeah.
It's still thermodynamics, it's still statistical mechanics.
Yeah, it's yeah. So basically, so what I'm going to do is, so in PT-symmetric quantum, in usual quantum mechanics, they have been able to come up with certain fluctuation theorems, and then I will generalize those to PT-symmetry and show what happens, and an application in optics. So here is the crux. So suppose you have a system, that's the original Dzerzhinsky paper, 1997 PRL, and you look at non-equilibrium work, and you look at many realizations of non-equilibrium work, and this is the free energy difference between two states. And if you take this average, so this difference is what we call irreversible work, is exactly equal to 1. So this is called, or this should be greater than or equal to 1, but under certain conditions you exactly get 1. So this is called classical Dzerzhinsky equality, which connects non-equilibrium work with free energy difference. Now this is a fluctuating quantity, so there is a notion of distribution of work, P of W, and then so you can define this average in this fashion. So that means if you want to calculate change in free energy in equilibrium, you must know how the non-equilibrium work distribution behaves for a given system, and this is valid for both slow and fast transformation, and it's also valid for closed and open systems. So basically this equality is a generalization of the second law, that the irreversible work should be positive. Okay. Now I'm not going to go into the lot of details, but people have done real experiments on, in this particular case, an RNA molecule. You stretch and you ask many times, you stretch and you ask how much work is done as a function of extension, and that's how you get the statistics for work in this system. And there are many other examples of calculating this. So basically, so this is the question. The problem is notion of classical trajectory is not applicable in these systems. So if you want the generalization of Zazinski equality to quantum mechanics, then you have to do something else, and this is the so-called two-time energy measurement, which means you prepare the system in a Gibbs state, you take measurement about the system, then evolve the system by some time dependent Hamiltonian, again measure its energy at second time. So this is the protocol called two-time energy measurement, and this has been discussed in the literature. So you can now define this or extend this to quantum work. So this is the initial eigenvalue of the system at a given initial state, then you evolve the system after time t and you measure this again. So this is the energy difference, and this is the quantum mechanical work of the eigenstate corresponding to these. This is how it is defined, and therefore you can then define a quantum mechanical work distribution in the following fashion, where these are the probabilities of those, the system being in state n and from n to m. So therefore you can extend classical Zazinski equality to quantum Zazinski equality in the following fashion, and then you can show that this works. So there's a yes.
I guess the second time energy measurement, you wait for the
Yeah, you wait for
the nullity.
yes, yes. You wait for a certain time and let the system evolve by time dependent Hamiltonian, and then you do that again. So this is the extension of Zazinski equality to simple quantum mechanics. Now the question I want to answer is, if I were to make it PT-symmetric, does it hold?
You need to be sure that this is less than the edge of the universe.
Of course, of course.
No, I didn't mean that facetiously. I mean, it can easily happen that the later time, the relaxation time can be just enormous.
You're right, and there are many papers trying to understand that question, and they have sort of settled that question, under what conditions you can do that. So what we have so far, so we have a generalized second law of classical and quantum systems. That's the Zazinski inequality, and its approach for isolated quantum system. So we want to extend it to experimentally relevant physical theory, which is the simplest realization of to open systems. Okay, so therefore we start with the PT-symmetric quantum mechanics, and we'll show how this generalizes. And thermally isolated systems with balance, loss, and gain. That's what I'm going to do in the next few minutes. And there are many and many applications to systems of this kind. Now this I'm going to skip to this audience because you know all about PT symmetry and the CPT norm. So here I write the generalized time dependent Schrodinger equation in the following fashion, and this is your C operator there. And then now you have to calculate transition probabilities. So this, in the PT symmetric quantum mechanics, the C operator enters here. Now U tau is the unitary time operator for time evolution. And then you have the PT operators. This is the initial density, and so state n and m. So you can actually write the transition probabilities in this fashion for a PT symmetric quantum system. So if you are in the unbroken regime, then you can calculate the exponential non-equilibrium work in the following fashion, and these are n and m are the eigenvalues that you evaluated at time 0 and later time with these probabilities, and then you put it in, and then you use the probability, notions of the norm, etc. You simplify all this, and then you will find. Well, let me go back. You will find that in the unbroken regime you will get the Zazinski inequality except that you have some gauge potential in the Schrodinger equation. This is very important. That depends on this C operator. Now you have already seen all this in PT symmetric quantum mechanics. So the question in this paper actually, so we can apply this formalism to this system. So basically for that system we can write that these two equations, and kappa is the coupling. So the equivalent time dependent Hamiltonian, now alpha is, gamma is the PT symmetric thing, and kappa is the coupling. So we can now write a Hamiltonian in terms of this operator like this. and now we can calculate the energy eigenvalues for this two level system. So, when alpha is less than 1, you are in unbroken symmetry regime, and when this is greater than 1, you are in broken PT symmetry regime. So, we take all that stuff and assume this is a protocol, we assume a linear protocol in this fashion, and now here I am plotting irreversible work, which is basically the difference between the non-equilibrium work minus the free energy difference as a function of this alpha. So, you can see that this in the Zazinski equality W minus delta F exactly remains 1. So, the equality is always satisfied, but if you look at the irreversible work as you approach the phase transition, the irreversible work diverges. So, this is like a critical point, but it diverges, but when you go on the other side it is still infinite. So, it is quite different from a quantum critical point that you see in systems where you look at the quantum susceptibility and it goes down, but here the quantum irreversible work diverges. That means the phase the response of the system is inhibited. If you go on the other side in the broken regime, so clearly the irreversible work here is the real part and the imaginary part. So, Zazinski inequality does not hold, and if you look at the work, irreversible work, again imaginary and real part, and they will diverge here. So, this is quite different than typical quantum critical points.
But how did you do the calculation there? You needed to calculate the C operator.
Exactly. Okay. So, what would
did you do?
so the C operator, the difference is in the unbroken regime you have commutator, in this case you have anti-commutator, and that is the fundamental difference.
Right. So
Yeah.
it behaves a little bit like fermions, which we know.
Yes. So, that is a fundamental difference how the C operator behaves in the two regimes. One it commutes, another case anti-commute, and one after, and that is how we calculated this. The C operator for this using the anti-commutation. So, this is quite different. What we are finding is quite different than what you would find in quantum critical points in typical systems. So, the irreversible work diverges from both sides, you see. So, it is not like a thermodynamic phase.
The C operator is divergent while not in
Diverges out. Yes.
alpha.
Yeah, here,
When you come on the other side,
yeah,
it's
he's,
still the continuation.
Right.
yeah, exactly. You see,
But
it's
it no
you,
longer commutes with PT.
yeah, it's going there. It's going there to infinity here. Yeah. So, anyway, so all the details are contained in this PRL. So, basically, there's still some issues. As I said, to do this calculation or to do even an experiment, you have to do this protocol two-time measurement. So, there are still some issues that for open quantum system, the stationary state is not Gibbs, and there is some discussion here. And two-time energy measurements on systems is not sufficient. This is the point you were making, and there's some discussion here. So, we need further solutions and generalizations of this problem. So, measure energy of the system and environment. So, now question of entanglement and others, but we do not know that. But there is some discussion in this paper, or find better definition for quantum entropy production, this whole bunch of. So, this is a very open and fertile field. So, I am going to stop here and just summarize this part. So, for small quantum systems, there are fluctuation theorem that came about last few years, which are a generalization of the second law of thermodynamics. Two-time measurements for isolated and open quantum systems is now more or less under control. So, one could think in terms of thermodynamics of PT-symmetric quantum mechanics. So, what I talked about, all the details of calculations are in this paper, and we are now extending it to relativistic systems, etc., but that is a story for another day. Thank you.
Could you explain a little bit more about in the second part?
Yeah.
Shredding equation. You
Okay, so
Hamilton. You add the C operator term. Yeah, that one.
you look at this paper. In this paper, they will show you that you need a gauge-dependent potential, which depends on the C operator in the Schrodinger equation. That's the key. So that's the key. Yeah. Yeah. That's your, yeah. So that's the key.
It's
Yes.
And also you allow C operator to be changing in time. If you want to maintain this too,
Yeah, it's
then,
time dependent.
unavoidably you have to change the Schrodinger equation to with that gauge term.
So without
that is the consequence of time changing C operator and unitarity.
yeah, so you
Time changing Hamiltonian.
Right.
Yeah.
For time changing Hamiltonian.
so without this you cannot solve this problem, and this without your paper we could not have done this.
Without that, you lose the either unitarity.
Yes,
or time dependence.
exactly. So this is the key here, and in the broken regime, the anti-commutation is the key, and then we are able to do this.
You also mentioned this Dzerzhinsky equality in the context of optics, right? So
Yeah.
What is the problem there, the statement? What do we want to understand?
Okay, let me show you. So this is two couple waveguides in optics. Two couple waveguides. So that's the simplest system. Let's see. This is the system we took as an example on which we could calculate all these things. So this was the physical system, two couple waveguides, and then we could calculate explicitly the C operator both for broken and unbroken regimes and could carry out all the.
Yeah.
Yeah.
But, I mean, it only anti-commutes
Yes.
in a very special case, and that's where you have a plus in the upper left-hand corner.
Minus, yes.
Exact
Yes.
plus and minus.
Yeah.
In general, it doesn't really anti-commute. It's just that it doesn't commute.
It generally doesn't commute.
Okay. Anyway, here is the plus infinity and here's the minus infinity,
But
and
this is in the
a very special case
very
where we
special
could do
case
that.
where it exactly anti-commutes.
Yes, and that's what we used for the broken regime. Otherwise, this was not. We were not able to calculate this otherwise. So yes.
No, but then that just raises a question, and that is, could you have taken a more general C that didn't commute with PT so that you could get something like the lambda point, where you do have
So the
it rises and then drops?
so the question is, what kind of commutation would that be?
Yes.
I don't know the answer to that yet.
It doesn't
But
have to be anything. It's not
It
required
neither
to be.
commutes nor anti-commutes.
It doesn't have to be anything particular.
It could be just the continuation
Of the previous, it should be the continuation of the previous one.
This one you mean?
Continue it to the broken.
Yes.
okay.
It should be the
Of course, it's
continuation.
no longer good one, but you take it.
No, this is something I like to discuss later because when we found this, we were very perplexed in the sense that we thought this is like a quantum critical point, but this is not like a quantum critical point. But now what you're suggesting is if we don't take that very more general thing, it could look like a quantum critical point. There may be a connection, but I don't know. I mean, so this.
There's also this question of whether you define the C operator in the broken regime by simply analytically continuing in the coupling constant.
And we didn't do that.
And the problem with that,
Was that?
this is PT Baldwin.
Somebody is trying to hack our computer.
What? What is it?
Somebody is trying to hack the computer. Vulnerability detected.
I don't see it here.
You better click on
It's a
options
false.
very.
It's okay. It's okay.
Um,
Yeah.
But the problem is, you see, if you simply analytically continue, then what you're doing is you can always analytically continue something that is analytic, but a commutation relation with a anti-linear operator like time reversal, that's not an analytic equation, okay?
Mhm.
Because it takes complex conjugate. So you simply lose that equation. Okay, now you can look on the other side of the critical point
And see.
ask what happens, and you can ask, does it commute or does it anti-commute? In general, it just doesn't commute, it does something.
Something else.
Yeah, it does something else, but it's not clear whether or not you go to the broken regime just by analytic continuation. You may want to start a priori in the broken PT-Symmetric.
And then ask what happened.
Establish a quantum theory there.
I see.
Just say
So,
yes.
so this was a very special case that we did.
That's
And
right. You did analytic continuation, but it may be that you don't want to do that.
Yes.
I just don't
you know, we wanted an answer, so we had to do something. Yeah.
That's fine.
Okay, Boris.
Yeah, I have a very simple question. You showed a picture of what you call Newton's cradle. Can you just...
Newton's cradle, okay. Now, where was that? That was in the beginning.
Okay, yeah, here actually usually as a cradle you have a chain
Okay. So here what is prepared is, so you have an anisotropic confining potential, and then you have a cloud of atoms with two different momentum, h cross k and minus h cross k, and then they oscillate.
Okay, but this means that this is sort of a cradle which is formed only by two particles?
Yeah,
That's the
Particle-
use of the terminology.
terminology is two different momentum. Is two. And this is a paper in which all the details are given in this Nature paper. So experimentally, and then you can imagine.
Okay,
Yeah.
there are some works where in terms of BC and nonlinear optics
Yeah.
alike, actually people consider clearly Newton's cradles which are built as chains of many solitons.
That's also
Really
possible.
it demonstrates the Newton cradle dynamics
Yeah.
functionally.
Yeah. So this is an experiment actually in which this is realization of quantum Newton cradle is.
Yeah, my question is if you don't use our time-dependent Schrodinger-like equation, rather two other approach. One is just using the Dirac Schrodinger equation and assume the Lensel dynamics of course is no longer unitary. And then will also be able to show the Jablonski equality have some.
That's a very good question.
open system.
That's a very good question, because here we assume that
Yeah, this is a closed system.
it has to be unitary or at best unital, which means there's a map. But if you go beyond that, then it's an open system, and I don't have an answer yet. And one has to.
Another question would be, there is another formalism rather popular, which is bioorthogonal physics. Which is
Bioorthogonal, yes.
bioorthogonal
Yeah.
physics, which is for generic, even non-PD, non-information system,
Oh.
artificially create a broad space, left stage, and you use right stage. That artificial creation you always give you unitary if you do the inner product between left and right.
Okay.
And the left stage follow the H dagger dynamics. I wonder if you using that formalism, what can you see? in this
Okay.
system?
So you'll have to give me the reference, and then we can go through and do this systematically to see what the consequences. Yes.
I'm not completely following the discussion.
Philip, where are your British manners? You asked for permission and you take it.
Well, thank you, sir.
Your Highness.
Apparently I've been given permission.
Okay.
Under sufferance. As far as I understand it, even if the Hamiltonian is time dependent,
Right.
the set of states at the later time is still complete.
Yes.
So if you use that as the basis, you must have unitarity. You don't have to do anything fancy. You're evolving a complete set into a complete set.
Unitarity is not guaranteed.
Well,
Is not
the
guaranteed.
eigenstates is no longer the solution.
Yeah.
Oh no, but they never had to be eigenstates. They only had to be complete. They don't have to be. They don't have to be eigenstates to be complete. They only have to span the Hilbert space.
No.
That doesn't take into account the
Yeah.
It is not following.
Yes.
completeness.
But going back to optics, so
Okay.
we're discussing just two coupled fibers, a simple system. So I want to see what is the question? What is the
Non-equilibrium system?
no? What is this work that in tangible terms? What are we going to measure in order to see whether this?
I mean, these are the equations. The field intensity is there. E1, E2, and then we can calculate. So this is the coupling.
What is the force? Where is the force?
What is the
Look,
Brzezinski quality?
okay. Basically, we take this, and this is the Hamiltonian. Then we can calculate the irreversible work relevant to this.
So he's asking what. So you take the derivative of some potential to get a force, and then you compute work. That's what he's asking.
Yeah.
So these fields evolve. It's kind of a trivial problem.
No, we just tried to illustrate on this example for which we could calculate all these things exactly. That's all. That was just a simple example as an illustration of the. But there are many open questions, including open systems here, and we don't have an answer yet, and we are thinking about how to deal with this.
But answer more loudly so we can.
Yeah, if I want to answer to Boris, I will tell him in simple terms that the Fatmer in Iowa, I think he will not benefit. it does not make tangible. It was an exercise.
That was an exercise to illustrate the point. Yes. Okay.
If there are no other questions, then we should be happy to thank the speaker again. And